Okay, good afternoon, everybody. Today we will continue our lecture on vector spaces, subspaces, and this topic will continue for today, and we are going to have a summary of the course, or we'll go through things after this break, next week's break. That course will just review entire topics of what we did to make sure that in the midterm, which will be the following week after that, you have a good and successful exam, okay? So I'm hoping to finish all these topics of vector spaces, subspaces, and all those, and how to obtain them today, hopefully. If not, there will be some more of it after your break, and then you will be ready for your midterm exam. I hope in midterm exam, everybody will be much more successful, okay? To start with, is there any question on vector spaces and bases and linear independence and those things? Anybody has any question to start with? Do you have? Yes. Okay. What is a vector space and things like that? Yes. Of course, I could finish this entire topic in one lecture. Then you won't understand anything. That's the reason we will explain to you from many directions until you understand. As I told you last class, linear algebra is something that you will always use in your professional life. It's not something that you see it once and you will never see it again. It's not one of those courses, okay? There will be some courses like that, few maybe, but they are still very important. But linear algebra will always be with you. In many of the courses, you will use these concepts, and in your professional life, you will use it more and more. Okay, linear algebra, importance of linear algebra is increasing every day. When people talk about artificial intelligence, etc., they are talking about linear algebra as well. Okay, so linear algebra will always be there, and it will be very important. So vector spaces. Okay. Let's make a summary of it as requested. Okay. So vector space is a set of elements. Okay, let's call them V1, V2, etc. A set of elements that satisfy the following properties. Okay? To call this set a vector space, it has to satisfy the following basic principle. I'm not going to write all the details on which I did a few weeks ago. Now I will give you the basic thing. First of all, let's call this a set V. Okay? If 0 is in that set, there is a 0 vector in that set. That's 1. 2, for every, let's say, x in V, there exists a unique minus V, such that V plus minus V is 0 vector. This 0 is not 0 scalar, this is vector, right? When you add vectors, I'm not writing, otherwise we used to write these things, okay? We don't use that, it's unnecessary, the context clarifies that, okay? So let me just make this picture so that you are very much familiar with this, x, y. This is the two-dimensional vector space. Okay, what we are saying is that there should be a 0. So a vector here is what? This is x, this is y. We call this a column, right? This is a vector. It has x component, y component. It's a column, and we call this a vector. So 0 is a two-dimensional vector, right? 0, 0. X is 0, y is 0. So therefore, 0 is in this set. For every v, let's call this v, there exists a minus v. So what is minus v? It is that when you add them together, you will get the 0 vector. What is that? You just take this one in the opposite direction, right? So this is minus x minus y. So when you add these two together, this is what you get. Okay? When you add, so 3, this is also very important. For every x and y in V, alpha x plus beta y is in V. Okay? So any linear combination of two vectors in that set, when you add them together, you multiply them with a scalar. Is this alpha a vector? No, it's a scalar, right? Beta is a scalar. These x and y, they are. These alpha and beta are defined in what? You remember? So it's a field, right? It's a field. Who said it's a field? Who said fields? I heard fields from somebody. You said. Good. Great. It is a field, right? So in abstract definition of a vector space, you have an underlying field. Okay? It doesn't have to be real number or complex numbers. It can be any very abstract things. It can be anything as long as it's a field. So we also talked about what is a field, right? So when you have a set of scalars, those scalars have to satisfy some axioms. Then we call that set of scalars a field. So we build our vector space on a field. Okay? So alphas and the components of x and y, they are in that underlying field. And here the underlying field is real number system. Okay? So two-dimensional vectors is, so when you add two vectors, right, you get, how do you add two vectors? Let's say this is one vector, this is another vector. How do you add them up? Okay, you just take, this is geometrical addition of two vectors, right? But mathematically, how do you add them up? X and y vectors, how do you add them? X1, y1 plus x2, y2, x1 plus x2, y1 plus y2. Right? This is how we define vector addition. How do we define? We discussed all these things before, that's why I'm not going through all of them. So alpha x is equal to alpha times x1, x2. So it is alpha x1, alpha x2. So basically, if you have a set of elements that satisfy these properties and the other detailed ones, okay, we call it a vector space. Okay? And we talked about, I gave you several examples of vector space. Let me give you a few more. Okay? The set of second order polynomials. I want to hear you. Is this a vector space? So this, we defined elements here, right? It's not, they are not arrows, like here. Is this a vector space? Please say yes or no, okay? Yes? Who says no? Okay. Why do you think it is no? This is, so, okay, let me clarify that. At most second order. So this set of polynomials with degree at most 2. That's what I mean. Okay? So is it a vector space now? Everybody agrees? Why? Because 0 is in a set of second order polynomials. What else? For every polynomial, for every second order or less polynomial, there is another polynomial that if you add them together, you get 0, right? How do you do that? Let me just, so 0, so this is, in general, this is what? Like A0 plus A1x plus A2x squared, right? This is a second order polynomial where determinant factor A0, A1, A2. So you have 3 parameters here. So 0 polynomial is what? Just 0. 0, there is no x. Okay? For example, if I give you this vector, this is v, what is minus v? It's just minus of this. Right? If you add 2 second order polynomials, multiply this by 2, and multiply this by 3 over 2, you get a second order polynomial, isn't it? Another second order polynomial. So this would be like, so 2, 9 over 2 plus x minus 2x squared. This is also a second order polynomial. So when you go through all these details, you see that this satisfies the axiom of being a vector space. Therefore, it's a vector space. Okay. What is a subspace? So let's call this V. So let me talk about U being the set of first order polynomials. Is this a vector space? The set of first order polynomials, it's a vector space, right? It is a vector space by itself. Okay. Is it a subspace of V? What is the definition of subspace? I give you have a vector space V, and I give you another set called, let's say, U, right? If every element of U is also an element of V, and U by itself is a vector space, then we call it a subspace, right? A subspace of, so we don't say this is a subspace, we say a subspace of V, right? For example, what other subspaces of V can you tell me? 0 is a subspace, yes. It says only, you see, a vector space does not have to have always infinitely many vectors, right? 0 space has only one vector. It's just 0. Okay, what other subspaces? Real numbers. Yeah, you could say that, yes. The real number, which is 0th order polynomials, right? Real number 0 is a real number, and all the real numbers are like you do not have this. Yes, real numbers is a subspace of that. What else? Second order polynomials themselves, right? Every space is a subspace of itself. So therefore, that is also a subspace. Can I talk about, for example, second order even polynomials? Are they a subspace? Polynomials that only have like A0 and x squared. They miss x. Do they form a subspace? They do, right? If you add any two even polynomials, you will get another even polynomial. So no x will crop in between them, right? Okay? So when you add them, subtract them, you're going to get another. Did you understand this question? Okay? How about odd degree polynomials? Second order polynomials with having only odd terms. Do they form a vector space? No, right? Because this, let's say x. So you have x, polynomial x, and you add it with something else, minus x, you get 0. So 0 is not in that set. 0 is not an odd degree polynomial. Okay. Yes?
You're saying that 0 is a vector?
Absolutely. 0 vector has to be in the set. 0 vector, okay? 0 as a scalar, of course it's a part of the field. So 0 vector, here for example, 0 vector is, so you have, in general, you have a vector that has x component, y component here, right? In this R2.
Vectors have to go somewhere.
So 0 is the one that doesn't go anywhere, it's just a point. Or it goes everywhere, but it has no magnitude. Yes?
You say singularity points?
Excuse me? Not singularity points. To talk about singularity, you have to have something else. 0 vector is a part of the definition that 0 vector is something that when you multiply any vector with 0, you get that vector, okay? So it is the 0 vector. So we don't talk about singularity or anything. When we talk about singularity, we will talk about matrices, okay? Okay. You remember linear independence, linear dependence? So let's say, let me write it there. So I will come back to this example. Linear independence. Okay. Let V be a vector space and V1, V2, VL be in V. Okay? So these are vectors. V1, V2, VL, these are vectors. Okay? V1 are called, this is definition, linearly independent if alpha 1 V1, alpha 2 V2, alpha L VL, this is 0 vector, right? Has alpha 1, alpha 2, alpha L is equal to 0 as the only solution. The only solution, okay? This is very important, the only solution. Do we have another one? Bitti. Okay. Okay. Let me just first discuss this here. Okay. This is much easier to illustrate this linear independence here. Okay. Let's say, see in R2, example, in R2, I have V1 is equal to 1, 0. V2 is equal to 1 minus 1. Okay? Very simple exam question is as follows. Are these linearly independent? Are these linearly independent? What do you think? Okay, how do we check this? We go back to the definition. Alpha 1, V1, plus alpha 2, V2 has to be equal to 0. Meaning, let me write this in the vector form. Alpha 1 times 1, 0 plus alpha 2 times 1 minus 1 is equal to 0, 0. So this 0 means 0 vector, right? So don't get confused. So if you just multiply these things, alpha 1 plus alpha 2 and minus alpha 2 is equal to 0, 0. So this will give you, second equation will give you alpha has to be equal, alpha 2 has to be 0. And this first one will tell you alpha 1 minus alpha 2, which is 0 from here. Therefore, alpha 1 is also 0. So alpha 1 and alpha 2 both has to be 0, right? This is the only solution. Okay, how about I just example 2. So V3 is 2, 5. So I have V1, V2, and V3. Same V1 and V2. Are these two vectors linearly independent? These three vectors. What is your guess? Are they linearly independent? Who thinks they are linearly independent? Who doesn't? So everybody thinks they are linearly dependent, right? Okay. Yes, they are surely linearly dependent. Okay. I will tell you why I know that offhand. Okay. So answer. Alpha 1, V1, alpha 2, V2, alpha 3, V3 is equal to 0. Okay, now let's write this in more explicit form to show the columns. Alpha 1 times 1, 0, alpha 2 times 1, 1, alpha 3 times 2 and 5. So first row gives you alpha 1 plus alpha 2 plus 2 alpha 3. Second row gives you alpha 2 plus 5 alpha 3 is equal to 0, 0. So what will you obtain from here? This one will give you alpha 2 is equal to minus 5 alpha 3. And alpha 1 is equal to minus alpha 2 minus 2 alpha 3, which is alpha minus, so this is alpha 2, right? This is alpha 2 and minus 2 alpha 3. So that becomes 5 alpha 3 minus 2 alpha 3, so it is 3 alpha 3. So for any alpha 3, you just take it anything you want. Just take alpha 2 5 times minus 5 times that, and alpha 1 3 times that. And this equation will be satisfied. So you have infinitely many solutions. Therefore, these are linearly dependent vectors. So let's go back to this question. So we define linear independence. Okay? So let me take V1 is equal to 1, V2 is equal to 2x, V3 is equal to minus x squared. Are these three vectors, are they vectors in this vector space? These are three vectors, right? These are three vectors. They are at most second order. So therefore, they are vectors in this vector space, second order, the vector space of second order polynomials. Okay? So when is this satisfied? Alpha 1 V1 plus alpha 2 V2 plus alpha 3 V3 equal to 0. So let's write this more explicitly like we did. Alpha 1, so V1 is 1. Alpha 2 is 2x. Alpha 3 is minus x squared, which is alpha 1 plus 2 alpha 2 x plus minus alpha 3 x squared is equal to 0, meaning 0 polynomial. Okay, so you put there identical. Did you use this before? When you put 3 lines like that, more than equal, they are identical. That means for every x, they are the same thing. Okay, so we are not. This is not an equation. This is an identity. That's what it means. So this is 0 vector, 0 polynomial. So when is this satisfied? When is a polynomial 0 polynomial? When is that? If all coefficients are 0, right? So therefore, this is true only if okay? So therefore, these 3 vectors, they are not arrows, but they are vectors. They are linearly independent. This is proof of it. How about another example? I add here another 4th vector. I add there as 1 plus x squared. Are these 4 vectors now linearly independent? Okay? Let me do that here. Okay, so alpha 1 V1, alpha 2 V2, now alpha 4 V4 has to be equal to 0 vector. Okay? So again, the same thing. Alpha 1 times 1, alpha 2 times 2x, alpha 3 times minus x squared plus alpha 4 times 1 plus x squared has to be equal to 0 polynomial, right? So this will give you from here, let me just continue here. Okay, alpha 1. Please tell me I will write. Plus. So what is this constant coefficient by the constant term? Okay, so x to the 0. What is the coefficient here? Huh? Alpha 1 plus. Very good. Okay, x. What is the coefficient? 2 alpha 2. X squared minus alpha 3 plus alpha 4. So when is this satisfied? When minus alpha 3 plus alpha 4 is 0, when 2 alpha 2 is 0, and when is 0, right? So this tells you alpha 2 has to be 0. Fine. It doesn't matter if one of them can be always 0, right? We don't want all of them to be 0. If all of them has to be 0, then it is linearly dependent. Okay, alpha 1 is minus alpha 4, and alpha 3 is alpha 4. So you have infinitely many solutions. So this equation has infinitely many solutions. Alpha 2, take alpha 2 equal to 0. Take any alpha 4, anything you want. Just take alpha 1, whatever you took, take minus of it here. And alpha 3 should be exactly the same thing. And it will satisfy this equation for every x. Okay. What else should I tell you about basic? Do you need another example on this one? Is it clear now? To this one example I want to give you again makes everything more clear. Okay? Is this a vector space? Abdul Fattah will remember that, so he shouldn't answer. Okay? Is this a vector space? Meaning, if I have two vectors in this, right? If I have, let's say if I have to, so we have to check whether the vector space axioms are satisfied, right? So is zero, does zero vector is a member of this set? 0, 0 satisfies this, right? So therefore, 0 is there. For every x, do I have a minus x that satisfies this? It does, right? You just multiply this with minus. So this is clearly satisfied. When you have 2 points, two vectors that satisfy this property, let's say you have x1, y1. So meaning 2x1 plus y1 is equal to 0, right? You have x2, y2, meaning 2x2 plus y2 is equal to 0. Then can you say that alpha, so let's call this v1, let's call this v2, okay, alpha v1 plus beta v2, is this an element of this set? Okay? Does it belong to the set? What do you think? It does, right? Just alpha x1 y1 plus beta x2 y2 is equal to alpha x1 plus beta x2 alpha y1 plus beta y2. So if you multiply the first one, alpha 2x1 plus y1 equal to 0, beta 2x2 plus y2 equal to 0. You add these two together, 0 plus 0 is 0, right? So you would have exactly 2 alpha x1 plus beta x2 plus alpha plus beta equal to 0. So therefore, their linear combination 2 alpha y1 plus their linear combination also satisfies it. So therefore, it is a vector space. It is a subspace of R2, right? Okay, let me continue. How about I have, again, xy, and I have x plus y is equal to minus 2. Is this a vector space? It is not, right? It is absolutely not. Why not? Absolutely. There is no zero vector. It violates every condition, right? What else? If you take any two vectors in this one that satisfy this property, when you add them together, it doesn't satisfy it as well. So it is not a vector space. I think this much of review is enough, so we can continue talking about where we left off. So last week, we talked about column space and null space. Okay, let's have a matrix A. A matrix A. a m by n. Okay? Example 1, 2, 3, 1, 1, 1, let's say. This is a matrix. If you take, let's consider now this is 3 by 2. If you take this mapping AX is equal to B, okay? AX is equal to B. Meaning, I take 1, 2, 3, 1, 1, 1. X1, X2. I have here what? B1, B2, B3. So the way we look at this is that we talked about in the second week, I think. We can look at this B as taking the linear combinations of the columns of this matrix A, okay? Meaning, let's just expand this. You have 1, 2, 3 times x1 plus x2 times 1, 1, 1. And you get B1, B2, B3. This is like a system like this, okay? It takes x's, okay, and gives out, okay, let's write this column vector, x1 and x2. It takes x1 and x2 and gives out b1, b2, b3. What is in here? This A is in here, right? This is the system. This is the input, and this is the output. This is how we can look at it. So this maps x1 and x2 into b1, b2, b3. This is the kind of mapping. The question that I asked last week, and we discussed it quite a bit, if I give you any b1, b2, b3, can you find the corresponding x1 and x2 such that when you take the linear combination of these two columns, you will get that one? The answer is no. But give me a candidate for which you can find an x1 and x2. So how can I pick b1, b2, b3? Okay, you can give me just one possible b1, b2, b3. 2, 3, 4. How did you obtain that? What is the solution? For which axis? Exactly. So this is how you get it. You start from x1 and x2, right? You take x1, 1, x2, 1, and that will give you 2, 3, 4. Okay? So if you start from here, for every x1 and x2, whatever b you get, you have a solution for it. As a matter of fact, you first cook the solution, then you obtain b, right? So it is the other way around. Okay, any other? 1, 1, 1. So what is x1 and x2?
x1 is 0, x2 is 1.
Okay, so how many such b can you find? Infinitely many, right? But, so this is what? In which space? These b's belong to where? In R3, right? So can you fill R3 with taking these linear combinations of this? So let's ask the other question. If I give you any b, can you find corresponding x1 and x2? The answer is no, right? Let's just arbitrarily pick a b and c. Let's take b is 1, minus 1, and 2, for example. I don't know if it has if I will be able to find x1, x2. I don't know that offhand, okay? So x1 times, so basically the question I am solving is 1, 2, 3, 1, 1, 1, x1, x2, and I want to b, this is B, this is A, and this is X. So AX is equal to B. But now we start talking about rectangular matrices, right? So far, we talked about always square matrices, where we had the same number of rows and columns in the matrix. Now we'll talk about rectangular matrices. You can have arbitrary number of rows and columns. They don't have to be equal. Okay. So the good old method, our aspirin, is Gaussian elimination, right? 1, 1, 2, 3, 1, minus 1, 2. So you perform Gaussian elimination on this one. 1, 1, 1. This becomes, so twice this is subtracted from here, right? 0, twice subtract from, so minus 1. Twice this, 2, minus 3. And this one, 3 times is subtracted from here, 0, minus 2. And this is 3 times, so 3. So this is minus 1. So this was my first pivot equation, right? So how do I proceed? Remember, in Gaussian elimination, you first want to take care of the first column. You want to make everything 0 except the first row. That's possible only if A11 is different from 0, isn't it? You remember this one. After we are finished, we go to the second column. Okay, we move to the second column. And we check A22, not A1. So we don't check the first row anymore. We check when you go to the second column, you move on the diagonal. You check the A22 element. If it is 0, then what do? We exchange rows, right? So this is not, so of course we don't do it here. We do it in the updated matrix. We do it whatever we have after the first phase is carried out. Wake him up. Wake up, man. Wake up, these are important. Okay. So first of all, I can just multiply this with minus 1. It doesn't matter, right? It's a part of Gaussian elimination so that we don't deal with unnecessary negative numbers. Okay. So but this is my second pivot. And I have 1, 1, 1, 0. And this 1, 3, 0. This becomes 0. Twice this is subtracted from here. And this twice this 6, 1 minus 6 is minus 5. So in equation-wise, what does this mean? This means 0 times x2 is equal to minus 5. And this means x2 is equal to 3. This means x1 plus x2 is equal to 1. So this tells us it is minus 5. This tells us it is 3. So they contradict each other. That means such a B cannot be obtained as linear combination of these two columns. Right? So that B. So I want to now talk about the subspace generated by these two columns. So it's clearly it doesn't fill the entire R3, right? So this subspace generated by these two columns does not fill the entire R3. Is it a vector space? Okay, what is it? So let's make the question is clear. I'm not asking about the solutions of this, okay? So let me go back. So does the columns of this, linear combination of columns of this, does it form a vector space? Yes. Why? It is 0. If you take 0 times this plus 0 times this, 0 vector. All linear combinations of these columns of space, 0 is there, right? You can take all linear combinations, say it's there. So it forms a vector space. Okay? It forms. So this is called the column space of A. So when do we have a solution for this equation? When do we have a guaranteed solution? If B is an element of the column space of A. Okay? Let's break for 10 minutes and we will continue. Okay. So column space of A is linear combinations of matrix A. CA is the set of all linear combinations of columns okay, if this is m by n, so what is this? This is a subspace, we said, and what is the space that this is? So what is it? So this has what? How many columns does it have? N. How many rows? N. M rows. Okay? So these vectors are what? How many dimensional vectors are these? M, right? So this is M. Okay? So these are columns with M components. So this is determined by the number of rows of this matrix. Okay? Okay, now let's talk about null space of A. So that is the set of x's that satisfy this equation. Okay? Is this a vector space? All x's that satisfy is a vector space. So what are we going to check? Let's do it together. 1. Is 0 vector included in it? Yes. 0, when x is 0, this is satisfied. Okay? If I have an x that satisfies this, let's say I have an x1 that satisfies this, I have an x2 that satisfies this, how about their linear combination? Is this satisfied? Why is that? Because of matrix multiplication. So A alpha x1 plus A beta x2. This is alpha comes out. So since this is 0, of course, we say here 0. Okay? Therefore, this is 0. So it is a vector space. Okay? Okay, what is this? This is called null space of A. So this is null space of A. Okay? This x's, what is their dimension? So this is subspace of what? Okay? This is, as a matter of subspace, we call it like this. Okay? Subspace is this. Okay? This is subspace of R. So number of So when you are multiplying this with x1, etc., what is this? N, right? So it has to do with the columns. N. Okay? So column space of A is a subspace of Rm. So it has vectors with columns with, let's say, V1, V2, Vm. And these are, let's call them U. So these are U1, U2, Un. Of course, I know I am repeating myself, but the idea is that everybody understands these things. There is no point. We will start talking about orthogonal matrices and orthogonal subspaces and all those. If you don't understand these things, you will just totally get lost there. So we have to make sure that these are very simple things. There is nothing difficult here, right? You just need to just look at it and try to understand it and ask if you don't understand something. Let's say I have a matrix A, 1, 2, 3 again, and 1, 1, 1. Okay? I want to now look at the column space of this. Okay? Column space of this matrix is linear combinations of, let's call this is C1, column 1, column 2, column 3, right? You just take all linear combinations of C3. Okay? And if you want to, so these all possible linear combinations of columns will form column space of A. Okay, how about null space? So that is AX is equal to 0. So we have to find solutions that satisfy this, and they are vectors in the null space. Okay? So this is 1, 2, 3, 1, 1, 1. X1, X2, X3. So this column space will be subspace of what? R2, right? It has to do with the number of rows. How about null space? Null space. This will be subspace of what? R3. Okay? I'm not saying this is three-dimensional. I'm not saying this is two-dimensional. I'm saying what I'm saying is that these vectors in these spaces, they have two components, and this one has three components. It has to do with the columns and rows of A. No great deal about it. Okay? So I want this to be equal to 0, 0. Okay? Let's just perform our good old Gaussian elimination again. So 0, 0 here, so I don't need to put it. So 1, 2, 3, 0. You just subtract that from here. Minus 1 and minus 2. Okay? So what we have is that this last equation, Ibrahim, can you read this for me? What does this mean? So I can just erase this as well, right? So this means what? Huh? x2, 2x3 is equal to 0. This means x1, 2x2, 3x3 is equal to 0. Okay? So this tells you that x2 is equal to minus 2x3. And you just use it here. x1 is equal to minus 2x2 minus 3x3, which is minus 2 that is equal to plus 4 minus 1. This is x3. So what this is telling us is that finding these solutions, this solution in general form is x3 and minus 2 x3, and this is x3. In other words, 1 minus 2, 1 times x3. So all of the solution, so we might as well just call this a C, right? Any constant C, just arbitrary constant. For any C, this vector, so AX is equal to 0. Okay, let's multiply it. So what do you have? 1 times 1 is 1. 2 times 2 is minus 4, so it is minus 3. 3 times 1 is 3, so it is 0. Okay, this row, 1 times 1 is 1. 1 times minus 3 is minus 2. 1 times 1 is 1, so it is 0. And this is satisfied for all C's, right? So this vector space, null space of A of this matrix is spanned by this vector. Meaning, by taking linear combinations of this vector alone, will give you all possible solutions that satisfy this. Okay, it spans it. I talked about this last week, so let me talk about it again. Okay, spanning a vector space. Let V be a vector space. And let V1, V2, Vn be n vectors in V. If any vector V in the vector space can be obtained as a linear combination of V1, V2, Vn, then this set of vector spans the vector space V. Okay. For example, the example we did here. Oh, you already raised it. Okay. If I give you 1, 0, and 0, 1, V1, V2. Can you write any two-dimensional vectors as a linear combination of these two vectors? It's so obvious, isn't it? We have been doing that since high school. So you can. As a matter of fact, you can write as x times v1 plus y times v2. This is, as a matter of fact, called standard basis for two-dimensional vector space. But is this the only one? How about this? v1, 1, 0, v2, 0, 1, v3, 1, 1. Does this set of vectors span R2? It does, right? I'm not saying that this is the minimum number of vectors. As a matter of fact, you didn't need this, right? As a matter of fact, any two of these is enough to span R2. Okay? For example, if I give you just arbitrary, so this is our second example, right? If I give you a vector, let's say 1, minus 3, how can I obtain it from here? One solution is, like, so alpha 1, 0, beta 0, 1, gamma 1, 1 has to be equal to 1 and minus 3, right? One obvious solution is, one solution is, as everybody will scream, is alpha is 1, beta is minus 3. But give me another solution. Okay, so I take alpha equal to 0 and gamma equal to 0, of course, yes. I take alpha equal to 0, let's say, okay? Then I have, what do I have? Gamma is equal to 1, and beta is equal to minus 3, it's minus 4, right? Beta is equal to minus 4. So take 4 times this is 4, 4, okay? I'm sorry, so 1, 1, this is minus 4, so this becomes minus 3, okay? So 1 and minus 3, so this satisfies it. How many other numbers I can find? Infinitely many, okay? Okay, so in this case you wonder, so and then what is this? We thought we had something good, then you brought us something else, it screwed up. So we call a set of vectors with minimum number that spans the vector space is called a basis, okay? Minimum, so let's write that here. Basis. Okay, I'm not going to write it in full. I say that a set of vectors with a set of linearly independent, that's what it means. This is a more beautiful way of saying that. Linearly independent vectors that span V is called a basis. Very nice, isn't it? A set of linearly independent vectors that span a vector space is called a basis. Yes? That's what it means. This is definition. Definition. This is basis. Span means, I'm sorry. Span means this one. You can obtain, I give you a set of vectors, okay? These vectors, I don't care if they are linearly independent or not, right? If I can get all of the elements of the vector space by taking linear combination of those, we say that those vectors span this vector space, okay? If that set of vectors who are spanning the vector space happen to be linearly independent, then we call it a basis. So that means that's the minimum number of vectors that do the spanning, okay? That are capable of spanning is called a basis, okay? For example, these two are these linearly independent? They are, right? So we did that before, but it's so easy. Let's do it again here. So V1, V2 are linearly independent. How do we know that? Alpha V1 plus, okay, beta V2 equal to 0, meaning alpha 1, 0, plus, I am doing it over and over and over so that you also do it over and over and over, so it sticks, okay? It's very important. It's because of quiz 1 we had. Okay, this is 0, 1, so this is equal to alpha, beta, 0, 0. So the only solution is alpha is 0, beta is 0, okay? So therefore, these two are linearly independent. We also proved that give me any xy, right? I can write it as a linear combination of these two vectors. Just x times v1 plus y times v2 will give you that vector, no problem. So therefore, this is a basis for R2. Is this the only basis? Can we imagine any other basis? Do you think this would be the only basis on Earth? You would have zillions of bases, right? Any two linearly independent vector would be a basis in R2. So just so that you don't confuse what is a basis and what is spanning, these three vectors, they span R2 as well, right? They span it. Just take, we can give me any vector in two-dimensional space. I am able to find the linear combination of these three that gives me any v vector I want. Okay? But these are not linearly independent. They span it, all right, but these three vectors are not linearly independent. So if you have a set of vectors that they span the vector space and they are linearly independent, that means we call them a basis. That's the definition of a basis. Is it clear what's a basis? Okay. Let's do another example on that one. Okay. So, example. V is given as the set of second order polynomials. We already discussed this is a vector space, right? Vectors. A set of linearly independent vectors that span V is called a basis.
The independent part is missing.
Linearly, yeah. My hand cannot catch my brain. Linearly independent vectors that span V is called a basis. What a nice definition, isn't it? So spanning, we already discussed it. So when they are also linearly dependent, so that's it. Okay. So this set of second order polynomials, can you give me a basis for this? How many vectors would you need in this basis for that spans all second order polynomials? Who will tell me that? Yes. But we are talking about polynomials. Second order polynomials. So give me the vectors. These are polynomials so that everybody understands. Okay, I think you are making an analogy. I can see where you are. Okay? Tell me the polynomials, so I will write them. Okay? So V1 is what? Give me a polynomial. So you have 1, okay? V2, x, good. V3, x squared. That's what you meant, right? So what he's talking about is this, okay? When you have a polynomial like this, a0 plus a1x plus a2x squared, you can just make a parallel with this. You can say that this is analogous to a0, a1, a2, right? So in science, you will have many examples like this. You have a matrix, you have another matrix, you multiply them, and that corresponds to multiplication of two rational functions of z, for example, okay? And they correspond to differential equations of a system, okay? So this analogy is important. This and this, they are analogous. So, but in terms of vectors, v1, v2, v3, any second order polynomial can be written in terms of these, right? So these three vectors span the vector span v, right? Meaning, if I give you any polynomial can you find a linear combination of these three vectors that will give you this? Yes, right? I just take minus 2 times v1, minus 2 times v1, plus 1 times v2, plus pi times v3. Again, this is a standard basis for this vector space. This is the most natural one. But it doesn't have to be like this, right? I could take it. I will just make something very strange now. Okay? I take this. V1 is equal to 1 minus x plus x squared. V2 is minus x plus x squared. V3 is minus 1 plus x, for example. I wonder if this is a basis. Okay? So it doesn't have to be like one of the vectors is 0th order, the other one is 1st order, and the other one is 3rd order, right? Or 2nd order. So it can be any vectors in the vector space. These are surely a member of the vector space. Isn't it? These are in the vector space, aren't they? So the question is, if I give you any vector like a0 plus a1x plus a2x squared, can I find alpha v1 plus beta v2 plus gamma v3 such that this is satisfied for any a0, a1, a2, right? If this is satisfied, then I will say v1, v2, v3 spans this vector space, okay? If they are linearly independent, then I will say they are a basis for this vector space. Okay? So alpha 1 minus x, I hope it doesn't require too much calculations. Beta minus x plus x squared plus, okay? So constant terms, alpha, there is no constant term here, minus gamma, okay? Power of x, what do I have here? Minus alpha, here, minus beta, plus gamma, and x squared x squared, I have alpha and beta. Am I right? Alpha minus gamma, x minus alpha minus beta plus gamma, and x squared, alpha, and gamma. So I need to solve this alpha minus beta for any A0 minus alpha minus beta plus gamma equal to A1 for any A1, and alpha plus beta is equal to A2, right? From these two, I have 2 alpha is equal to A0 plus A2. So alpha is A0 plus A2 over 2. Then beta is equal to A0 plus beta is equal to alpha minus A0, and gamma is equal to, yes. What? This one? Alpha minus gamma. Here? Alpha, beta, gamma. Here? Alpha, beta. Here? Okay. Alpha minus gamma, yes. Yeah, it was too easy, isn't it? Good, Ibrahim. I'm glad you caught that. Okay. So you solve this, okay? Most probably it will turn out to be, this is like your homework. Work it out, okay? So meaning, for any A0, A1, A2, if you can find alpha, beta, gamma, that gives you another set of vectors that span it. Then what are we going to check? If these are linearly independent. Do we know if these are linearly independent? We did it already. They are linearly independent. So therefore, this is a basis. And how many vectors do you have in that? You have 3. So therefore, you have 3 vectors. If they are also spanning, that means they are also a basis. Okay? So let's continue with our matrices. Where did we stop? Spanning a vector space, okay. So when we take this vector, A is equal to 1, 1, 2, 1, 3, 1. This has a column space, right? Column space is spanned by the columns of these. Okay? So there is a vector space here, and it is defined as all linear combination of columns of A. So what do we say? this CA is spanned by the column vectors of A. Okay? So what is a basis for that vector space? So what are we now talking about? So this set of vectors that span a vector space does not mean that they are linearly independent, isn't it? As a matter of fact, these are linearly dependent. So how are they linearly dependent? So we just check it. Alpha 1, 1, beta 2, 1, gamma 3, 1. Did you check it already? We didn't. Okay. So let's look for the solution of this, isn't it? If they are linearly independent or not. So we are checking. Okay. So this is alpha plus 2 beta plus 3 gamma. And this is alpha plus beta plus, this was 3, 0, right? No. 3, 1. 2, 1, 1, 1, okay. Plus gamma. So this is 0, 0. So this tells you alpha plus beta is equal to minus gamma, and this tells you alpha plus 2 beta is minus 3 gamma. Okay, take alpha from here. Alpha is equal to minus beta minus gamma, substituted here. So that is minus beta minus gamma plus 2 beta is equal to minus 3 gamma. So this is beta is equal to minus 2 gamma, right? And you substitute here, alpha is equal to minus 2 gamma minus gamma, so it is gamma. Okay. So therefore, these are linearly dependent. We knew it already, right? In two-dimensional spaces. We discussed it a few minutes ago. All you need is just two vectors to span entire R2. Okay? So what is a basis for? How do you compute a basis for this? Okay? This is today what we are going to talk about, different subspaces of A, related to A. We define based on A, okay? So column space, null space, row space, and left null space. And how do you compute basis for those? Okay, that's what we will talk about. Okay, we have 10 more minutes, let's continue. So what we do is, we perform Gaussian elimination. Let me just take that one. Okay, how to obtain basis for subspaces. I will just work it on some examples, then I will give you a general theory of that. Okay. So you are sending them to me as a messenger? Okay. So you take this, 1, 2, 3, and this is 0, minus 1, and minus 2. Okay, this is pivot number 1, and just multiply this with 1. This is pivot number 2. So what was rank of a matrix? Who remembers from last week? What was the rank of a matrix? Number of pivots, right? So rank was rank of A, definition is in Gaussian elimination, number of non-zero pivots. Okay, so the first pivot was first equation. This number is non-zero. We perform that. We come to second column. This is also non-zero. So this is rank 2. Okay, theorem. Rank of column space of A is equal to R. Okay, meaning you just determine the rank of your matrix A, okay? The dimension, by the way, the dimension of a vector space is the number of vectors in the basis, okay? Number of vectors in the basis of a vector space is called the dimension, and that is also the rank. So the dimension of CA is equal to R, okay? So the dimension is the number of, the number of vectors in the basis. Number of vectors in a basis. Okay? Dimension. Any question on this? Okay. So let's talk about now null space. You see, I am giving you all these different examples other than matrices so that you don't think vector space has to do always with matrices, okay? It is not. It is much more general. But matrices are very, very intimately related to vector space also. That's another thing. Okay, null space. So null space of A so when you have AX equal to 0, so this X has what? This is A is, let's say, A is M by N. Okay? So the dimension of null space of A is what? It's not N. It's a subspace of N. So it is N minus R. Okay? For example, when we look at this here, okay, let me continue this example, okay? 1, 2, 3, 1, 1, 1. I will just continue here. So I want to find the null space. So I want to find the set of all solutions for this equation, isn't it? So when I perform this Gaussian elimination, what does that mean? I multiply this with some E1 from here, right? Right? So it doesn't change. This was the whole thing, the thing about Gaussian elimination. If you perform row operations, it will not change the solution of the equation. It will change the equation. but not the solution of the equation. Therefore, when you perform this, solution of this is the solution of this, I'm sorry, is the same as solution of this, right? So you obtain here 1, 2, 3, 0, 1, 2, x1, x2. Okay? Equal to 0, 0. These are called pivot variables. Pivot variables. And these are called free variables. Yes, x1, x2, x3. x3, of course. Yes, absolutely. Yes. x1, x2, x3. It's raining. It's so beautiful. Okay? Can I continue here one more step to make my life easier? Okay? So I just make one more operation, row operation. I just subtract twice this from this first one. It doesn't change, right? It's the same as multiplying with another non-singular matrix from here. So what do I have? 1, 0. Twice this is subtracted from this. So this is 3 minus 4. This is minus 1, 0, 1, and 2. Okay? 0, 0, 0. Okay? So I have the solution now. So what do I have here? x2 plus 2x3 is equal to 0 from the second equation. And from the first one, what do I have? x1 minus x3 is equal to 0. So take x3, we called it free variable, right? Take x3 free. So x1 is x3, and x2 is minus 2x3. Okay? Then how do these things look? x1, x2, x3. That satisfy this equation. General form of them are x3 minus 2x3 and x3. In other words, it is 1 minus 2 and 1. That's it. Times x3. Okay? Free variable. Free parameter. So, do I have any other solution other than this? Meaning, does this vector together with this x3, do I get all solutions of this system of linear equation? Do you think there is any other solution other than the one that I obtained here? If there was, I would find it, right? So there is only this solution. So this, how many do I have here? Infinitely many. Is this a vector space? Is this a vector space? Does this define a vector space? Does this span a vector space? Okay, let's use the word. Is it a basis? Why? Because it's just one vector, right? So it's certainly it is linearly independent. There is nothing, there is no other vector. So a vector by itself, it is linearly independent, of course. It spans the entire solution set. So therefore, this is a basis for the null space of B. So it's the basis for, so an A is spanned by 1, minus 2, 1. So this is a bit more complicated than the column space, right? In column space, you just say you have the columns, all linear combinations of the columns give you the vector space. But here, the null space is spanned by this, this vector we just obtained. Okay? Yes?
Can you repeat the definition of null space?
Null space. Definition of null space is, where did I write it? I erased it. Null space is here. Yeah, here it is. Yes. Null space of A is all set of all x's that satisfy this. Okay? Set of all x's that satisfy this is called the null space. Okay, let's stop for 10 minutes, then we will continue. So for a given A, M by N matrix, we have the following four subspaces. Okay. One, now this column space of A. All linear combinations of columns of A. Okay? We talked about this last lecture. 2, null space of A, all of the solutions of AX equal to 0. Okay? This is the null space of A. 3, row space of A, which is all of the rows of, okay, these are rows, okay, the vectors here are rows, okay. So all linear combinations of the rows of A. You call it RA, which is equal to column space of A transpose, okay? And 4, what is the fourth one? Left null space of A, which is the solution of, or the set of solution, the set of all solutions of X transpose A is equal to 0. Okay? Okay, A is a matrix with n columns, M rows. Okay? Therefore, CA is a subspace of, so this has how many, the vectors in C, how many components do they have? M. So therefore, this is a subspace of Rm, m-dimensional vector space. And A, how many components does it have that multiplies this? This is a subspace of R n, right? How about row space of A, which is null space of A transpose? This is subspace of what? So this is how many components you have. So what are you taking here? You are taking linear combinations of the rows of this, right? So X transpose A is equal to Y. So you are multiplying this from left, okay, by row vectors, taking linear combination of columns and obtaining linear combination of the rows to obtain a row, right? So this is Y transpose. So let me call this also Y transpose. Okay? So row vector. So just example 1, 2, 3, 4. Okay? 1 minus 2. You multiply this. What do you obtain? So 1 minus 6 minus 5. 2 minus 8 is minus 6, for example. Okay? So taking all linear combinations of the rows, you obtain a set of vectors, okay? Set of all these vectors, like this is same as the column space, right? But looking at now, instead of looking at the linear combination of the columns, here we are looking at linear combination of the rows, which is the same as taking the transpose of this, meaning making rows into columns, and look at the linear combination of the columns of A transpose, okay? That's why I write this. So this is, what is the dimension of here? M. This is how many? This is 2 by 2, so it doesn't represent that. So this is n, okay? So column space of A is subspace of R to the M, okay? This is clear. Okay. Let's do an example. An example that is not square, okay? Yeah, if we didn't transpose, see, column space of A, this was a subspace of Rm. So transpose has, this has m dimension, this has n dimension, because instead of columns, now you have the rows. Okay, you have m rows. Let me just write this example. Okay, A is equal to 1, 2, 3, 4, 5, 6, 1, 1, 1, 1, 1. Let's see, okay? 5, enough, okay? 1. Okay, yes?
The last row, RA equals NA transpose?
Yeah, not A, CA transpose. Of course, CA transpose. What is this? Yes, absolutely. Good, so he studied. Okay, so what do we have here? See, column space of A is what? The members of these are like what? things like what? This, right? So this, what does the set include? Give me some examples. 1, 1, right? 2, 1. Any linear combination of this, right? Okay. So all columns and more, right? So this addition of these two, subtraction of these two, etc. So it includes this kind of things. So it is the dimension of the vectors that are in this, they look like the columns of A, right? So therefore, this column space of A is related to the, so how many components do you have in those vectors? Same as this, like M by N. So M here is 2. N here is what? 5. Okay? So this is subspace of R2, right? So when you talk about now null space, so null space, you are multiplying this with x. How big is the x? Same as x1, x2, x3, x4, x5. So these vectors live in 5-dimensional vector space, isn't it? So what is 5? 5 is n. Okay? So null space of A is R5. Now let's talk about X transpose A. Meaning, so what should be X be? It should be 2 by 1, right? So this is X1, X2 times, okay, let me write it here, X1, X2 times this, right? Okay, so this result will be what? It will be something like this, isn't it? X1, it will be something like X1 so linear combinations of these, okay? Let's say 1, 1. They will be look like this. So this linear combination of these look like what? This or something like this. So these are, we take all linear, like we did here, we take all linear combination of these columns to obtain the column space of A. Now we are taking linear combinations of these rows. So this will live in okay. So this will be like this and more of that, right? Many combinations. It could be just one row as well, right? Then you would have one-dimensional subspace, but it's a subspace of R5 because it has 5 components, right? And left null space of A, okay? Did I give it a special letter? Let me see. I didn't. Left null space of A, which is null space of also A transpose, right? So in this case, what are we looking for? We are looking for X transpose times A is equal to 0, okay? What are the dimensions of this X? How many components does it have? X1 and X2, right? So it has to do with the row. So this is, so null space of A transpose is a subspace of R2. Okay. Is this clear? So these dimensions and take it up here so you can see it easier. So the dimension of CA is equal to R. Okay? R is the rank. R is the rank of A. Okay? And this is all same as CA transpose is also R. Okay? So the dimension of null space of A is going to be what? No, it's not 0. We are now talking about in general. Okay? So it is n minus r. The example we did I erase it? That one there, right? Not that one. The example I just erased. It's when you have 2 rows and 3 columns. We were able to obtain one linearly independent vector, right? It was written up there somewhere. So the rank there was 2. Remember? You just look at your, it was end of last lecture. We performed Gaussian elimination. We also went backward. We obtained an identity in the first part, and we had a free column. Okay? So R is 2. You have 3 columns, so n is equal to 3. So let me do another example instead of talking about like this, okay? A is 1, 2, 3, 4. So, okay, I will just make this 2, 4, 6, 8. Okay? So here, M and N. What is M? 2, N is 4, right? Let's perform Gaussian elimination on this one. So what do I have? 1, 2, 3, 4. And this is 0. Twice this, so this is 0, 0, 0, right? So how many pivots do I have? 1. How many free variables do I have? 3. These are free variables. And this is my pivot. So we have 1 pivot, therefore R is equal to 1. Okay? So therefore, my column space is one-dimensional, right? My column space is one-dimensional here. It's one-dimensional. That means there is only one vector that spans it, as a matter of fact. So with 1, 2 spans, so this 1, 2 spans CA. As a matter of fact, it's a basis as well. So it is also a basis. So what is the dimension of the null space? Dimension is n minus r, which is 4 minus 1, which is 3. And we have 3 variables here, right? So what is the basis for the null space? We will get to that in a minute. Okay? Let's continue. The dimension of the row space of A is equal to R, which is equal to 1 again. Isn't it? As a matter of fact, 1, 2, 3, 4, 5. So this is 1, 2, 3, 4, 5, spans the row space. So if there is only one vector, so the basis has only one vector. Okay, it's a line in multidimensional space. 4, 5, it's 4. Right? So, so in 4-dimensional space, this is just a line passing through the origin that spans the row space of this matrix. Okay, this one is again another line in 2-dimensional space passing through the origin. Also, that line spans the column space of it. How about left null space? Of A, the dimension of it, the dimension is equal to, what is that equal to? M minus R, right? M is 2, so this is 2 minus 1. As a matter of fact, can you please tell me basis for left null space of this matrix? What do I multiply this with? And it will give me, okay, it will give me 0. Okay? So X transpose is equal to what? I will multiply from left here. Huh? What is that? What is that? Minus 2 and 1, for example, isn't it? So multiply this minus 2 at second row, you will get 0. So this spans the left null space of A. Okay? Is it clear? Now I want to give you the general theory of how to obtain basis for all possible these 4 null spaces, okay? And I'm going to give you also a handout for that. I prepared a nice handout that I studied all these in detail so that there is no confusion about it. Yes?
Written in the top of the board, dimension CA equals R.
Right.
And the transpose equals R.
Yes, absolutely. So the rank of, what is dimension? Dimension is the number of linearly independent, maximum number of linearly independent vector you can find in a vector space, right? For example, in R10, if you have a subspace that has, for example, can I define in R10, okay? Let's talk about here in this small space. I have 10, okay? And I define a set of vectors 1, minus 1, 1, 0, 0, 0, 0, 0, okay? Okay? This is my subspace by define, and it's spanned by this. What is the dimension of this subspace? 1, right? So what is the dimension of a vector space? It's the number of linearly independent vectors in that space, okay? You remember we gave many examples. It is a subspace of R10, of course. So don't confuse this. So the dimension of this vector space is 1. It could be 0-dimensional as well, right? If I give you a 10 by 10 matrix that is non-singular, what is the dimension of the null space? There is only one solution for AX equal to 0, isn't it? So therefore, it is 0. Dimension is 0 there. So there is no dimension. There is only one vector in that one that is 0 vector itself. Okay? So it could be, so the greater space could be any dimension, but your null space or your column space or your row space could be any number less than that, depending on the structure of the matrix. What is the determining factor in that one? When you look here now, it's written. What determines the dimensions of your column space and row space and null space and left null space? Rank, exactly. So rank of the matrix is extremely important information about the matrix, and that determines what are the dimensions of different subspaces related to A. Okay? R is the one. And it is so easy to determine, isn't it? When we were a student 30, 40 years ago, Gaussian elimination was not that widely used in determining so many things. So the way I'm teaching you, this course is just, everything is Gaussian elimination, right? Everything. Rank is that, and I will now show you how you get the basis and everything. Everything is reduced to that beautiful, very simple, very intuitive Gaussian elimination. The Gaussian elimination is everything. It gives you everything you want reveals everything about your matrix. Okay. Let me go to that board. So I will give you general methodology to obtain basis for all these 4 subspaces. Okay? So, methodology. If you understand this, then there is nothing left for you to get confused about what is subspace and how do I get this and that. Methodology for computing basis for subspaces. Okay? You are living in the most important time of the course. Okay. So, first, given A, obtain LU decomposition for A. Okay? So what is LU decomposition? I give you A, and you know that we can almost always obtain LU decomposition of that matrix. It doesn't have to be square. Okay? I'm going to do an example on that one. Okay? If it is not possible, then what do you do? Special case requires PA LU. So we will study this afterwards, okay? But for the time being, we will assume that this is possible, okay? Then we start talking about one, null space of A. Okay? How do you obtain a basis for null space of A? Okay? Okay. So, you know L is a matrix like this. 1, 0, 0, 0, L2, 1, 1, 0, 0, right? L3, 1, L3, 2, etc. It's a square matrix. It has 1 in the diagonals and everything. Okay? And U is not a square matrix. It has the same dimension as the matrix itself. Not necessarily a square matrix. In general, it is like U11, U12, 0, 0. What are these zeros? These are matrices as well. These are zero matrices with appropriate dimensions, okay? What is the dimension of this U11? It is R by R, okay? It's R by R. And then this would be what? You have how many columns? M by N, right? So this dimension of this is N minus R, and this is N minus R by N minus R, etc. Okay? Why is it like this? Okay, how this is useful? Let me just, so let's compute now. So what are we trying to find? AX is equal to 0, isn't it? So let me write this in terms of LU decomposition. LU X is equal to 0. Since L is invertible, right, I can just multiply both sides by L inverse. So therefore, you have, this is identity, so you have Ux is equal to 0. Okay. So what this is telling us is that null space of A has nothing to do with L. It has to do only with U. Okay? And U is something like this. So U11, U12, 0, 0. Okay, this is X1, X2. So these are free variables. Okay, these are the pivots, right? Pivots. Corresponding, let's say, R of them here. Okay, this is N minus R of them. So this is 0, 0. Okay, so this is R and M minus R. Okay. So U11 X1 plus U12 X2 is equal to 0. And the second one doesn't give you anything. So this tells you that U11 X1 is equal to minus U12 X2. X1 is equal to minus U11 inverse U12 X2. Okay? How many of these do you have? How many free variables? These are free variables. This is telling you that we have no condition on X2. You can pick X2 any way you want. How would you pick them? How many of them do we have again? So we have M rows and N columns, right? So this has rank N. So this X will have dimension what? This will have dimension N, right? It's multiplying. It has the same number of columns as this. So this times that. And the resulting matrix has row M row. The resulting vector will be in M dimension. So this N and M is confusing, but we have to go over and over and over. Okay? I can also make mistakes. You correct me. Okay? So what we are doing is clear, right? So how many different ways I can pick this X2? I can pick it as 1, 0, 0, 0, right? Let me pick it standard. Then I can pick it as 0, 1, 0, 0, and 0, 0, 1. I can pick it how many different times? M minus R different ways I can pick it, isn't it? N minus R ways I can pick it, N minus R different ways. How many free columns do I have here? R of them are pivot columns. Okay? How many columns do I have in total? N. N minus R. n minus r free variables I have. So these are r pivots, this is n minus r free variables. I can pick them. So I can say the following. I can pick this, obtain an x1 corresponding to that one, right? That will give me a basis. I can pick this one, obtain. Instead of that, I can just make this capital X 1 and say U11 inverse, U12, and this is I n minus r. Okay? So once you perform LU decomposition on your matrix A, you have the basis ready for you. That's it. That's it. Let me do an example on this. It will make it more clear. You see how useful is LU decomposition, isn't it? It just reveals everything about the matrix. So I will give you an A is equal to 1, 0, 0. I will just give it with LU decomposition performed already, okay? So this 2, 1, 0, 1, 1, 1, minus 1, 2, 2, minus 1, 1, 3, 0, 0, 0, 0, 0, 0. Okay? So this is L, this is U. So L is 1, 0, 1, 1, 0, 0, minus 1, 2, 1. The partition I did is with respect to R, okay? Why is it R? Because you have only 2 pivot columns here. Everything else is 0, right? So you cannot, when you go to this column, there is nothing to pick because there is nothing here to, everything else is 0. So there is nothing to cancel, okay? So this is L11, this is 0, L21, you never have this, L22. And U is 2, 1, 0, 1, 1, 1, minus 1, 2, 2, minus 1, 1, 3, 0, 0. So this is U11, U12, 0, 0. Okay? So what is this telling me? The basis, so the basis is what there? N minus r times n minus r vector, right? It's a matrix. So U11 inverse, so X, this matrix is, the columns of this matrix is the basis for the null space of A, right? So this is minus U11 inverse, U12. So U11 inverse is what? So U11, 2, 1, 0, 1. How you compute the inverse of this? This is, you just switch this and switch the sign of this and divide it by the determinant. Okay? So you don't have to do it, you can just do it yourself. Okay, this is equal to 1/2 minus 1/2, 0, 1. Okay? So U11 inverse U12 is equal to 1/2 minus 1/2, 0, 1 times U12 is what? This. 1, 1, minus 1, 2, 2, minus 1, 1, 3. So this tells me that second row will remain as it is to minus 1, 1, 3. The first row, you just, okay, I will take this 2 out somehow, okay. So you just subtract the second row from the first one and divide the result by 2. Okay, so what is this, Ibrahim? So this is minus 1, 2, minus 2, minus 1, divided by 2, so it is minus 1/2, 1, minus 1, minus 1/2. And you multiply this with minus, okay? Then this becomes plus, this becomes minus, this becomes plus, this becomes plus. This minus, this plus, minus, minus. So what this is telling me is that the basis is very beautiful. It is, let me write it up there. Let me bring this down. So x is x1 and x2, right? So this is, we took it as I n minus r. So this is going to be, can you tell me that? 1/2 minus 1, 1, 1/2 minus 2, 1, minus 1, minus 3. So this is going to be 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1. So the null space of A, which is given with that LU decomposition, is spanned by this. Okay? So how do we check this, Husni? How do we check it? So you just multiply that matrix, multiply that U with this. What do you get? 2 times 1/2, right? First row of U, right? 2 times 1/2 is 1. Then 1 times minus 2 is minus 2, so it is minus 1. Let's do the running sum. Okay, 1 times 1 is 1, so it becomes 0, and the rest is 0. So this first column, when multiplied by A times X, it gives us 0. Okay, how about the second one? So 2 times minus 1 is minus 2, plus 1 becomes minus 1. 0 times 1 is 0. 1 times 1 is 1, it becomes 0, and the last 2 is multiplied by 0, 0, it gives you 0, right? So what I'm telling you is that A times X is going to give you a 0 matrix, okay? Meaning LUX, if UX is 0, of course, multiplied with L is also 0, right? So UX is 0, you can just verify that. Okay? I will just keep you today for 10 minutes. I want to complete. I want to give you also other subspaces as well. So it's very nice and concise. Next class, we will continue. We will do more examples on this, okay? But I want you to have this before your vacation. So let's look at left null space of A. So let's talk about left null space of A. So left null space of A. How do we compute a basis? That's the name of the game now, right? So we want to find X transpose A equal to 0. What are the general solutions of this? So I want to find the entire set of solutions for this, right? So again, X transpose, I write here LU is equal to 0. Okay? So let me call this Y transpose. Okay? Since L is immutable, I could as well talk about Y transpose U equal to 0. Meaning, we are looking for all solutions of this. Once I find Y transpose, okay, then what is X transpose? Then I find X transpose L is equal to Y transpose. You remember LU decomposition? This is how we were doing it. So you first solve for this, find all solutions of this, then solutions of the X's are related to Y's through this formula, okay? So we can continue and do this as well, okay? So Y transpose U is equal to Y1 transpose, Y2 transpose, U11, U12, 0, 0. Next class also asked me why this is always 0, 0 here. I mean, couldn't we have U22 here? Okay, let's respond to that. This should be equal to 0, 0, right? So you do this multiplication. So Y1 transpose U11, then this is 0, 0, I'm sorry, 0, 0. Y1 transpose U12 is equal to 0, 0, okay? From here, U11, U1. So what will this give you? Y1 transpose U11 is equal to 0. That means Y1 transpose is equal to 0. Okay? And Y2 transpose, there is no Y2 transpose. This tells us that Y1 transpose has to be 0. Okay? It doesn't give us any condition on Y2. What does that mean? Y2 is free variable, isn't it? So you can take Y2 anything you want. Since it is being multiplied by 0, isn't it? You can take it anything you want. Okay? So Y2 vectors are free variables. Okay? So I come back here. Okay? So I have X transpose L is equal to Y1 is 0. This is Y2 transpose. Okay? So let me continue next class. It can take me another half an hour. I'm just, maybe you have a train to catch or something. But it's very beautifully works out. Maybe I'm not going to wait till the class. I might just send it to you and you can just post them. So we'll continue next class. We'll go through each and every one of these and you will see that it's a very beautiful theory that's behind this. Okay?